In this video I'll be talking about gamma ray spectroscopy and how it's used to identify materials and how they decay, about the processes that occur to create the peaks that are seen in these spectra, and the detector and its calibration, and some spectra of known sources, including a mixed preparation source at the end. What actually is gamma ray spectroscopy? Gamma ray spectroscopy is the process of using a scintillation counter to detect the spectra of a material from the gamma rays emitted from a radioactive source. We can plot the number of gamma rays detected against the energy they're detected at to produce a spectra. The spectra for a given source is unique to what that source is and is used to identify it. How are gamma rays detected? Gamma rays are absorbed through the photoelectric effect. Photons, in this case gamma rays, travel into the scintillator and hit the scintillation crystal. The photoelectric effect then occurs. Since gamma rays have momentum, when they hit the scintillation crystal, they can knock electrons off the surface of the scintillation crystal, giving off photoelectrons, which are seen as small flashes of light by the photocathode. These flashes of light are detected by the photocathode, which then produces an electron that is sent through a focusing electrode onto some diodes. The diodes produce secondary electrons to amplify the charge received as a signal. These secondary electrons hit more diodes, which produce more secondary electrons, amplifying the signal even further, so that the scintillator is more sensitive to low numbers of gamma rays. This is really important when looking for rare decays. The electrons finally hit the electrical connectors that absorb the charge, sending a signal to the computer. This charge gives the bin number of the gamma ray that hit the scintillator, and has to be converted to an energy to finally give what energy the gamma ray that was incident had. To reduce the uncertainty of what energy the gamma rays had, and increase the sensitivity of the results, the entirety of the photomultiplier tube is a vacuum. This means that the gamma rays and the electrons don't interact with any other particles, potentially losing energy. Moving on to how gamma rays are produced. Gamma rays are produced in four primary ways. Way 1 is the direct emission of gamma rays from the source as it decays. Way 2 is pair production from antiparticles emitted by the source annihilating to form gamma rays. Both direct emission and pair production can very clearly be seen from the decay spectra, so usually that's what we look at first. The decay spectra doesn't give the peaks formed from the other two ways that we're going to move on to. The third way is Compton scattering, from when gamma rays hit electrons in the scintillation crystal, scattering off them and creating different energy gamma rays. The last way is in kernel conversion, where an atom emits an electron and leaves the atom in an excited state, and characteristic X-rays are emitted as the electrons fill the vacant states left by the ejected electron. We're going to discuss these ways in a bit more detail in the next 4 slides. Direct emission is when the radioactive source decays by emitting a gamma ray that we can detect. Most of the peaks that are visible in the spectra are caused by direct emission, and it's the easiest process to check for since the energies of direct emission are so very clearly seen from the decay schemes. In this case, sodium-22 gives off a 1.275 megaelectron-volt gamma ray as it decays from its excited state to reach the more stable neon-22. Pair production. Pair production is when a particle and its respective antiparticle interact and annihilate, giving off a large sum of energy. This energy can be in the form of gamma rays. The pairs in this experiment are from an electron and a positron annihilating one another. They produce 2 gamma rays of 511 keV, which is the rest mass of an electron, given by the ever so famous equation E equals mc squared. Compton scattering. Compton scattering is the relativistic, inelastic scattering of photons by electrons. As the gamma rays hit an electron, they are scattered off with a new energy that's related to the angle they were scattered at. This means that for each large peak we detect, there is a smaller peak created by the Compton scattering, with the intensity of the peak being related to the number of possible electrons a gamma ray can scatter off. For this video, the detector is the same for all spectra examined, so the chance of observing Compton scattering is the same for all large peaks. The energy of gamma rays that have been Compton scattered is given by this equation, where E0 is the energy of the initial gamma ray and m0 c squared is 511 keV, coming from the rest mass of an electron. We can say that gamma rays are most likely to be scattered directly, so theta would be 180 degrees. This means that we have the most likely energy of a Compton scattered photon to be this. Internal conversion. Internal conversion is probably the most complicated of the four ways of producing rays. Note that internal conversion does not actually produce gamma rays, it produces X-rays that are also detected by the scintillation detector. Internal conversion is the process of when an excited state of an atom loses energy by ejecting the atomic electron closest to the nucleus. This is most likely to be the 1s electron. As all the other electrons in the atom drop to the next vacant state left, the electrons shift to lower states so that the 1s state is filled. This shifting of energies gives us characteristic X-rays that can be looked up in a table to determine what source caused them. This is the end of the theory section, so now we can move on to talking about the practical elements of gamma-ray spectroscopy. Now, let's talk about rays, baby. Let's talk about peaks of E. Let's talk about all the features of the spectra that we can see. Let's talk about the practical side. Calibration. Calibrating the energy for spectroscopy is done by taking a known source with a known spectrum and defining the bins such that the features of the known experimental spectrum match up. Here we can see experimental bins matching up with the known energies for a sodium source. The main consideration in a calibration process is that the bins will only match up to the correct energies close to the range between these calibration features, so for much higher or lower energy particles, the calibration won't give accurate bin energies. These matched up bin energies are constant for all sources, so we can use these to find the unknown spectra features for unknown sources. Now we're going to analyse the spectra of three sources, sodium, cobalt-60 and a mixed preparation that we have bought from the internet. Sodium. Sodium is useful for a calibration source since its spectrum is so simple. There's three features, a peak at 511 keV, a peak at 1275 keV and a noisy region for energies lower than 300 keV. Looking at the decay scheme of sodium, we can see that it decays into positrons and relaxes from its excited state by emitting a 1275 keV gamma ray. These positrons undergo pair production, so they produce two 511 keV gamma rays. So the decay scheme accounts for all peaks, so we don't have to consider Compton scattering or internal conversion as possible candidates for the peak. Cobalt-60. The uncalibrated region is given by the peaks of the sodium spectrum we did before, so any peak that's far from the region of 500 to 1300 keV will not be calibrated. Examining the cobalt spectrum, we can see three sharp peaks, a 200 keV peak in the uncalibrated region, and a 1170 keV peak and a 1330 keV peak, both in the calibrated region. Following the three analysis steps of first checking the decay scheme, then Compton scattering, and then finally internal conversion, we can get a good guess of what the peak candidates are. Looking at the cobalt-60 decay scheme, we can see that it decays by two emitted electrons which won't be picked up by the detector, leaving it in two excited states. From these excited states, it emits gamma rays of 1173 keV and 1333 keV to decay to the more stable nickel-60. This explains our in detailed peaks 1 and peak 2, as we can see on the graph. This leaves us with the 200 keV peak, sharp peak. It's not in our decay scheme, so we have to consider the other ways that the peak is formed. We use the Compton condition to find the energy a photon will have after it Compton scatters off an electron. A photon scattered off peak 1 will have an energy of 210 keV, and a photon scattered off peak 2 will have an energy of 215 keV, as seen by our equation earlier on in the video. These Compton scattering values are near to our peak of 200 keV, so they're most likely of the cause of this peak. Since both peaks have such similar Compton scattering energies, the peak produced by them should be quite intense. This explains why the 200 keV peak is so large. Since all the peaks are now explained, we don't have to look at internal conversion for this spectrum. Examining the mix preparation in detail. Mix preparations generally have a more complicated set of spectra than sources from the pure materials, so calibration has to be done for a full range of energies so that we can examine all the features in detail. Having been given that the mix preparation has cesium-137, strontium-90 and Am241 in it, we can use gamma ray spectroscopy to confirm this. Looking at the decay spectra for all the components, we can see that SR90 decays only by emitting electrons, so it won't be picked up by the spectroscopy at all. CS137 decays by emitting gamma rays that will show up and electrons that won't, and Am241 decays by emitting alpha particles that won't show up and gamma rays that will show up. This means that we can expect to see peaks because of the cesium and the Am. From the information sheet printed about the mix preparation, CS is more radioactive than Am, so that we can expect that bigger peaks will be related to the cesium and smaller peaks will be related to the Am. The decay schemes give that peak D is caused by the CS137 transitions, and peak B is due to the Am241 transitions. Peak D being more intense than peak B is expected, since CS137 has a much higher count rate than Am241, as given by the information about the mix preparation. Peak A might seem like it comes from the just from the Am241 direct transmission, but that isn't the whole story, so we're going to save it for later. From peak D, we get that E scattered is roughly 180 keV, which means that peak C is most likely a Compton scattering peak coming from peak D. From peak B, E scattered is roughly 50 keV, which doesn't actually reveal a peak. Peak A is the most interesting peak of the lot. Checking the decay scheme, you'd initially think that peak A is just due to the direct transmission of Am241. But if we check the probabilities of each transition, we can see that peak A can't just be a direct transmission, since that's half the size of peak B. This is where internal conversion finally shows up. Checking the characteristic X-rays of CS137, we can see the EK alpha X-rays have an energy of 32 keV. This is roughly the same as the 26 keV of peak A. So both the direct 26 keV Am241 transition and the EK alpha X-rays that come from CS137 produce the peak, explaining why the peak is as intense as it is. So to summarise, we've talked about the theory of gamma ray spectroscopy, how the detector and the production of rays works, and the practical side of gamma ray spectroscopy, calibrating the detector and analysing the spectra of sodium-22, cobalt-60 and a mixed preparation. This concludes my video about gamma ray spectroscopy. Hope you've enjoyed it and have a great day.